Thank you, and let me also thank the organizers for inviting me to this exciting seminar and for giving me the opportunity to speak here. Today I'd like to complement earlier presentations in this seminar where it was discussed how we can exploit symmetries of semi-definite programs by matrix star algebras. In this talk I'll try to exploit the numerical efficiency by sparsity structure and by iterative methods, and the main point that will come up is conditioning numbers, how we can handle those. So I like to start with a historical survey, trying to understand why those developments that we have seen so far did happen and what we might want to concentrate on in the future. I will then discuss ill conditioning in linear programs and show how the ideas that we have for linear programs can be transferred to semi-definite programs. And then in a point 2 plus epsilon, I want to address an epsilon progress that I'm trying to move on into an augmented Lagrangian approach, but that is very ongoing work, so I wouldn't deserve a separate point. So when we look about the history of methods that prove to be numerically successful, we start with the simplex method. And later on, we have seen the simplex method had effects, for example, in the division of active set methods. But so this is essentially the starting point. Then in the 1960s, people developed barrier methods and penalty methods, and they were summarized in the book by Fiacco and McCormick, SUMT, Sequential Unconstrained Minimization Techniques. And one of the methods, for example, in today's language, you would say it's a dual interior point algorithm. But at that time, it was not successful, partly because of ill conditioning and partly because computers only had single precision. Later on, with double precision, that would have been slightly better. So then the augmented Lagrangian method followed, a method that I will come back later, and SQP method, where I don't have to say much, it's a successful algorithm. But I like to continue with the work of Carmacher in '84, who first addressed linear programs. And even though linear programs is a very simple problem, we can see that the development for linear programs really influenced then later on the development by Nesterov and Nemirovsky self-concordant barrier functions. And today this is a little bit forgotten, but this is the most general approach we have for convex programming. Almost anything that we know, p-norm or exponential or logarithms or anything that we can express can be modeled by a self-concordant barrier function, and even problems that we don't know how to express. So it is known that there exists a self-concordant barrier function for the co-positive and the completely positive cone, except we cannot compute it. But this is really the most general approach, and I just like to briefly outline the ideas. So when we have constraints fi of x less or equal to 0, they are modeled by a barrier term minus log minus fi, and then the self-concordance, the only property that is needed in order for a barrier method to work, is that when we look at the logarithm of this function and then only restrict it to a line, so L of t, the only thing we have to make sure is that for any strictly feasible x in any direction h, we have these two inequalities where theta is some constant, some positive constant. So if we can verify that this here is uniformly valid, then we can apply the whole interior point technology from Nesterov and Nemirovsky. And the nicest application known to everybody is when we have f of x is a polynomial of that x, is the determinant of a matrix x, then the function L of t can be developed by using the Cholesky factor when x is positive definite, and then factoring the Cholesky factor, you see that the product of the determinant is a determinant of the product, so we can take the log L out. And I forgot always the determinant. Yeah. So imagine that was a determinant. Yes. So there's supposed to be determinants in there. And here is no determinant anymore. So here we can see this breaks down to a sum of linear factors, each of which we can easily verify the self-concordance for fixed value of lambda. So this is the very short and nice proof. And actually it carry over to so-called hyperbolic polynomial, something that Daniel Blaumann reported on earlier in this seminar. And the great virtue of interior point methods, the theoretical convergence is independent of any condition number of the problem that's given there. So we have a fixed rate of convergence no matter whether there's ill conditioning or not. In the present time, coming up with with huge data, often sparse structure, people have moved on solving the linear system by iterative schemes such as the conjugate gradient method, or for symmetric indefinite systems, the so-called quasi-minimal residual method, which is a natural generalization of the conjugate gradient method for symmetric systems, or actually even for general non-symmetric systems, but it exploits symmetry if it's available. So the advantage, of course, is we don't have any fill-in by using those iterative methods. In theory, we have finite termination of conjugate gradient, but that's only a theoretical and not a practically relevant issue. When you run the iterative method, typically you see that the convergence behavior is something like superlinear. So the finite convergence often is not observed, but you see that after a while the iterative scheme becomes faster, and of course it's cheap. The main disadvantage is we need some form of preconditioner for many applications. And a very successful approach of this scheme is the program STP-NAL by Qin-Chuan To, Cao and Defeng San. And so also earlier in this seminar we have seen the new developments like subgradient method or conditional gradient by Frank, which is similar to the Frank-Wolf algorithm. And for me, the most annoying fact about this is those simple algorithms, they are almost optimal in the long run. But yeah, I'll come back to that later. So when we look at this brief history, I think there will be maybe three aspects that the hardware dictates the algorithms, of course. So in the beginning, the simplex method would give you an exact solution. Later on, the interior point methods, they have local superlinear convergence behavior under suitable assumptions, can solve medium scale problems. The conjugate methods, the iterative methods for linear systems, strongly depend on condition numbers, and the subgradient methods for the future definitely will do so too. So the accuracy that we are receiving from exact to superlinear to the accuracy tends to be decreasing. We get less good approximations, and the proximal size is increasing. So in particular, the discussion and analysis of condition number will remain interesting. Then coming back to the failed attempt of the sequential unconstrained minimization technique, it probably also had to do with the fact that not all the theoretical aspects have been understood in the early times. So the self-concordance telling us that the log is the right barrier function, this was not identified. So the sequential unconstrained minimization, they had all kinds of barrier functions. They had also penalty terms, and the primary dual interpretation of the central path was not recognized at that time.
They didn't log it as a choice.
Yes, but there was a choice. But they wouldn't say this is the one to take. Yes. And the analysis of rounding errors, I think there's still some work to be done. And finally, of course, there's some fashion always. So if some people do it, other people join in. But actually, I don't think this is the dominating aspect, but it's definitely it's there. So, like we have seen that the Karmakai algorithm had a great influence on the work of Nestor and Nemirovsky. I also try to give an example where we can learn from linear programming, trying to transfer it to semi-definite programming, and then yeah. So this will be a little bit technical, the next few slides, but I try to try to motivate.
Before you had a question, moving on with the crowd. Let me understand this. Means the crowd is now dropping IPM?
I think it's going to happen. Yeah. For the large-scale problems.
No, this is ahead of the crowd.
The crowd will be moving in this direction.
So this means dropping IPMs is ahead of the crowd, but soon you will be.
It's a question mark, so I'm not sure, but I could imagine this is going to happen. And so the linear programs, the primary dual system, so this is the standard form linear program. The primary dual system can be written with the diagonal matrix X, and some vector x times s equals to mu times e. This is the central path equation. And if we want to solve this system for a given value of mu and for a given starting point x, y, and s, then the linear system that we come up with has this structured form. This is quite well known to everybody. When solving this system for large-scale problems, we might be interested in using iterative methods. And for iterative approaches, I like to avoid systematic cancellations in the right-hand side when we transform the system. And I'll explain what I'm talking about, what I'm referring to with systematic cancellation error. Then, of course, we like to have systems with bounded condition numbers, otherwise the iterative methods will be very slow. We like, of course, to maintain the sparsity structure. Those 3 points are definitely the main points. Symmetric systems for iterative solvers have two advantages. First of all, the symmetry can be used in each single iteration, so it makes the half expensive. And also it is known that systems which are non-normal, so those systems, then the convergence does not only depend on the distribution of the eigenvalues, but also on the distance from normality. So a system that is not normal would generally have higher number of conjugate gradient iterations. And of course, if we can have a positive definite system, that would be most desirable, but it is out of reach. So when we look again at this system, for a standard system for interior point methods, we see that the system contains three diagonal matrices: the identity, the diagonal matrix X, diagonal matrix S, and the natural thing is to eliminate either the variable delta X or delta S using this the diagonal structure that is essentially for free. And so either way, any of those three options, when you do the elimination and some rescaling, you end up either with this system or with this system here. So with this system and either this right-hand side or this right-hand side. So whether you pivot over X or over the identity, after you rescale, it both will come up with the same system here. So, but still we have two choices, and both choices turn out to be numerically unstable, because we know in the end X and S will converge to matrices, to vectors where some of the components will be 0 and others are non-zero. So X will have some small entries, and when I have Q minus X inverse R, the information in Q is pretty much lost because the X inverse R dominates the whole thing. And the same when we have S inverse R and there's some components of S are really small, we lose the information in P. So this is the standard reduction, but when we see this, we actually find out this reduction can be combined, and we pivot. We take the large element of X for here and the large element for S for here, and because they're complementary, this is just a suitable way to pivot this. And while here, this is what we would refer to as a systematic ill conditioning. So you would know in the end you will get cancellation error. So this is something we want to avoid. This will always happen, even for well-conditioned problems. So this is the part to avoid. If the condition number is bad, then there's nothing of the problem. There's nothing we can do about. So if some of the X in the optimal solution tend to be fairly large, we have to live with that. But the systematic cancellation can be reduced. So we only take the inverses of the large component of X and the inverse of the large component of S, and then we do the same computations, and we can up with the same system where the standard linear algebra shows that that's the way we have to solve the system. So the matrix happens to be exactly the same, only the right-hand side is slightly different. Now, it's an evident fact that such a reduction, they can be rewritten as a matrix factorization. I will show that in a minute. And the condition number of the reduced matrix, of course, when we have a submultiplicative norm, cannot be worse than the condition numbers of the two factors that we have involved there. So since the reduction is stable for any right-hand side, we always have a bounded right-hand side. So since the reduction is stable, the reduction must be reasonably well conditioned, and therefore the reduced matrix must have a condition number which is comparable to the one of the standard system. And so just to mention, if we go from this reduced system and we take the reduced system is here, we have one more diagonal matrix, so we can do one more elimination over this diagonal matrix. This is what usually is done for most of the interior point methods that have direct solvers. We come up with this reduced system, and here, no matter what we do, we always have cancellation errors. They tend to be not so severe because direct solvers are fairly accurate, but we do have systematic cancellation here. Now, when we generate some small size examples, so 100 by 200 dimension, and we use A as a unitary matrix, first of all, this will be motivated by later on by the extension to semi-definite programming, and second, it also reduces some of the ill conditioning due to the problem. So we just use unitary matrix X, A, and X and S nearby the central path. Then when we just record the condition numbers that we get here, the normal equations are bad, but not that bad. What turns out, the stable reduction is extremely bad compared to the standard system, 10 to the 4 and 10 to the 12. And this is just the opposite of what I had stated as an evident fact in the previous slide. So the stable reduction is terrible. And the matrix factorization, actually, if you really want to write it down, you can define projections P1 and P2, and then you see this here is the system that we really solve. So this is the system with the original right-hand side, and then here this is the back solve for delta X and delta S. So here this system essentially corresponds to the stable reduction, and when we try to, because here now we include this artificial variable u, so we include the variable u also in the standard system, artificially including it there, so we have the same dimension. And now we can actually find the standard system, here the stable reduction, and if we find the transformation matrix that transfers them, we see the transformation matrix here has an x1 inverse. There is a large, so if x is tiny, then x inverse will be a large component. So this transformation matrix is poorly conditioned, in spite of what I claimed in the evident fact. In the evident fact, I argued that the right-hand side is not increased, so this matrix cannot be so terrible. But if we go back to the right-hand side, this has a very special structure, the right-hand side, and it turns out when you multiply this right-hand side with the transformation matrix here, then the huge components of this matrix X, they just cancel out. So there is no contradiction. You just have to be a little bit more careful than when first deriving this evident fact. And so, yeah. So now, since we're having an ill-conditioned system, we could think about taking a diagonal scaling where the diagonal has almost zero. So the S2 is large and X2 is tiny, and here vice versa. So both matrices, the X and the S, are singular in the limit. And if we rescale a system with matrices that are singular in the limit, we would expect that things get even worse. So that's the second evident fact, and of course it's wrong. So when we rescale the system, then we do come up with this system here, just as a straightforward linear algebra, and we can do a stable backsolve. So the backsolve only involves the large quantities of X of S. The X is a matrix which has at most ones on the diagonal, and the S, so there is no magnification at this point, and there's only some cancellation error in Q2 because the X1 So in any case, all the cancellation errors that come up here, they are recovered in the back substitution. And when we now look at the condition numbers of the standard system and of this rescaled reduction, actually we find out that the rescaled condition number is even better than the original system. It's symmetric, and we have a stable elimination of all the variables. So this here actually turns out to be the system of choice if we want to apply iterative methods. And for some reason, when we look at the condition number of the optimal basis, it turns out they seem to be fairly they seem to be fairly close to each other. Here there was just a rounding effect. This was 304 and this 305 or so. So actually, the conjecture was maybe in the limit those two could be the same, and then you can make this a theorem. So if the linear program has a unique optimal solution and some technical assumption is satisfied, then the condition number of the standard system of the scale reduction converges to the condition number of the optimal basis. And of course, that's the condition number of the problem, and you cannot expect to get any better than that. So, yeah, this is actually telling us this scaling is the best possible. And any talk in mathematics should have a proof, and this here is very short. So you just sit down and write the equations. And so just I'd like to return to the second evident fact. So when we look at the standard system, actually when in the limit, when some of the entries of x go to 0 and the others of s go to 0, in the limit this will be a block triangular system when you reorder it. And so the cancellation error that comes up here concerns the part delta x2 and delta s, and they are stably recovered, so you can actually solve the one block first and forget about the right-hand side of the second block, and then by the back substitution, which is stable, you don't have any ill conditioning anymore. And it turned out we can also look at small degenerate LPs, so where we have 80% or 20% of the basic primal variables are 0 and 20% of the dual variables are set to 0. And it turns out the condition numbers of the scale reduction actually are even better in those sample runs. So it really seems to be the reduction of choice if you want to apply iterative methods. So now that was the linear part, and the question again is, can we somehow learn from this for the interesting problem, namely for semi-definite problems? And so again, the semi-definite problem has the same form: linear objective, linear constraints, and a non-negativity constraint. And yeah, so the standard definitions. And
sorry, Florian, you cannot use standard preconditioning for the LP because it will destroy sparsity.
I don't know which preconditioner to use. If I have a...
The iterate, you have everything. You have the system.
I have the system, yes.
So
but for PDE, somehow there's always naturally associated a coarse grid or something that I can use as a preconditioner. So they have preconditioners for many of the problems coming from physics. But here, since the LP is a random, arbitrary structured problem, there is no concept known to me where I have a general preconditioner. So if I had one, this would be really great. We could solve all these problems, and I eliminate the question mark and I stay with interior point methods. So
okay, so the problem is you cannot have a structural precondition.
I don't know of any. Yeah. Thank you. Yeah. Yeah. And so for the semi-definite program, a similar problem structure and the standard notation. So the constraints are by scalar products A1 to AM and the dual operator, the conjugate. And so it's also quite known by now that we use a symmetrization operator in the last equation. So the central path is defined by the symmetrization applied to x times s. And so these here would be the central path equations, and it's almost the same as in linear programming, except in linear programming we had a diagonal matrix x times a vector s, and now here we have the symmetrization operator. And when we look at the linear system that we obtain by linearizing again, then we see again the structure is pretty much the same. And earlier we had here a diagonal matrix S and here a diagonal matrix X, and now these are those symmetrization operators that come in here. These operators are bad because they typically make the normal equations dense. So no matter what you do, the normal equations here don't allow a sparse factorization anymore. And so therefore, for semi-definite programming, iterative methods are even more interesting. search direction we follow up here is the Nestor-Todd direction, and so the operator depends on some matrix P that we can still choose, and so Nestor and Todd have been defined P in such a way that when you scale S with W to the half, so which means with P inverse, then you can come up the same scaling X with the P, and this is the matrix E, which is close to the identity, or mu times the identity. And when you do this, then it turns out, so the one operator SP times X delta S then can be written by, so this here we consider as some kind of diagonal scaling. We scale from left and right with P, and this as a Lyapunov operator, so we can easily find out that the SP can be written as the Lyapunov operator applied to the diagonal scaling of delta X. And the nice thing, and this is why we have the special choice of P, we can do the same thing to X delta S. So here's delta XS, and here the other way around, and the only thing changes, we have P inverse instead of P here. So that is the property of the Nestor-Todd direction I like to use here. So then we simply replace the symmetrization operator by these two operators, which are the same, and L is easy to invert, so we can put this on the other side. So we have LE inverse, and E is a reasonably well-conditioned matrix close to the identity, so there's no cancellation error here when we multiply by square root of mu. And P and P inverse have the same eigenbasis, so therefore we can use a unitary transformation and actually make these matrices the diagonal and put the unitary transformations here to the delta X and delta S. So we come up with a system that we have A times U and U star times A star, and here now we have a diagonal scaling with a diagonal matrix lambda and lambda inverse, and here we have new variables U star delta X. And this matrix here, now this is exactly the same sparsity structure as for linear programs. We have so this here essentially is a diagonal scaling. This is this is exactly a diagonal scaling. So we have a diagonal matrix, another diagonal matrix, the identity. So now we are back in the linear programming situation, and we can try to use the same ideas. And so in particular, so this scaling here, we can write it. So this means we multiply from left and right with lambda, or it's the same thing as component-wise multiplication with this rank 1 matrix lambda transpose, the diagonal matrix. So so when we use iterative schemes, so this is an artificial variable, so we don't have to compute A star U. So typically A is sparse, and if you compute the operator AU, this would be a dense operator, but we don't compute that, so the only thing we need is we know how to apply U, and we keep the sparse matrix A. And then now we're trying to use the same definitions, and the one change that we have here compared to linear programming, it was evident either X goes to 0 or S goes to 0 in the strictly complementary case, and exactly one of those two is going to be small. Here, those matrices lambda, when we come back in a minute, some of the entries will go to 0, other ones to plus infinity, and other ones will be constant. So we cannot separate into two complementary sets anymore. And therefore, this slight generalization that we need here is, rather than pivoting a small x and a large s, we say we take 10% of the x and 90% of the s, and this will be a 2 by 2 block pivot. And since the system that will come up in the end is exactly the same, the 2 by 2 blocks, they don't really destroy any of the sparsity. So this is the main idea behind the reduction coming up here. So when you do all the formulas, you can come up again with a reduced system, and except from this L inverse that I will just talk about in a minute, except from this L inverse, this is exactly the same we had for linear programming. And now the choice whether I'm pivoting over over X or over S, this choice influences the residual. So I get a different residual whether I pivot over X and S. And essentially, the residuals in all cases, they have to satisfy this equation. So that's the equation. Any choice of R1 and R2, because R2 comes back in the back substitution. So any choice of R1 and R2 satisfying this equation will do. And this freedom of choice. This is exactly that I can choose whether pivot over X or S. And now, which pivot should I use? And now go back to the linear programming. In linear programming, you have seen if we choose a bad pivot element, a tiny pivot element, then the right-hand side will increase, will be huge. So we multiply the right-hand side with a x inverse, a small x inverse, and the right-hand side explodes. So since I don't know any better, I'm taking now the dual approach. I'm trying to choose the pivoting so that the right-hand side is going to be small. And then assuming that this pivoting actually will reduce the cancellation, and in numerical experiments it really did. So so minimizing, so we minimize the right-hand side subject to the previous constraint that we need to have, and you can write down the explicit formula. So it's given by this equation here, and so substituting for the partition into x1 and x2 from the linear programs. So the question is, this is now the same result as for linear programs, and unfortunately, when we look at this diagonal rescaling, let me see, this was a couple of slides ago. So here we have lambda I times lambda j. This is these are the elements that are component-wise multiplied with m, and so when we look at these components, then some of the lambda j squared, they will go to 0, or lambda I squared, some of the lambda j go to infinity, and some of the mixed products, they will go to a constant value for some I and j. So this partition is no longer possible, and actually we have a systematic increase in the right-hand side by 1 over cube root of mu or 1 over square root of mu, depending how you formulate this. So the result is slightly worse, but nevertheless, it dramatically reduces the norm of the right-hand side compared to any other pivoting strategy we have. So we tried this in some semi-definite programming instances. So we cannot compete with the SDP NAL. So part of that is certainly that we have only used MATLAB routines, no mesh files or anything. So our implementation is quite crude at this point. But also, we really are missing a preconditioner. So this is something, in some examples, and I'll show in a minute, the preconditioning really kills us. So the good example was we generated very sparse semi-definite program, 6 non-zeros per row in the matrix A, and then the dimensions from 20 to 2000, and the number of constraints from 100 to 100,000. And so we only had 10% accuracy for each search direction, but nevertheless, by doing the suitable step length control, the final accuracy was somewhere here in the order 10 to the minus 7. So those problems can be solved, and by using the fact that this matrix A star typically allows a sparse Cholesky factorization, we can always enforce that the primary dual equations are almost fully satisfied. These instances happen to be strictly feasible, so that's why the feasibility is always achieved at the end. And the running times is up to 2 hours here in this case. So those are at least acceptable running times. We tried the same thing for doubly non-negative examples, so for the cone with non-negative matrix entries for each of the matrices. And here, these results are rather disappointing. So we only get up to dimension 300, and even then we take like 3 hours on a standard laptop. And when we look, actually there was several iterations where the number of QMR iterations was huge. We stopped after 40,000. If we stop after 10,000, the whole thing diverges. It doesn't work. We really need, in the middle, we need many QMR iterations. In the end, the QMR was fast again. So here, this is where we really had to recognize the limits of this approach. And so, nevertheless, I just like to point out, so this problem means that we have those 9,000 entries, so half of that would be 5,000, 90,000 entries, so 50,000. entries must be non-negative, and so this is a reasonably large problem.
The correct M.
Yeah.
Estimated the M.
And so the M is just, it doesn't make any major contribution. So the bad thing is those non-negativity constraints. And yeah, so we really think, it really seems that those linear constraints kill this approach as long as we don't find a good precondition. No? And recently I had an application of linear programming coming from a biological application that had quite many variables. Right now we have been running an instance with 10 to the 7 variables, and the sparsity structure was really awful. So you have identity matrices of size 1,000 or 5,000 stacked in a row, and then another row and another row. And so this was only one of the blocks. There are 7 types of constraints, and each of which had a terrible sparsity structure. And we have implemented the whole thing matrix free, so the matrix has never been set up. Loop free, so in MATLAB we don't use any loops, and that was horrendous work. But now it runs on a standard laptop in about 4 hours, but it's still in a debugging state. So this is why I'm calling this 2 plus epsilon. Here the results seem to be much more promising for this approach, but it's based on this augmented Lagrangian with a conjugate gradient method to solve the linear systems. This is the wrong direction. So for now, I think I will be trying to continue this work with the augmented Lagrangian for large-scale problems. What we can see is either way, the augmented Lagrangian and also the interior point methods, they use smooth subproblems to approach the solution. And both for interior point method and for the augmented Lagrangian method, we need to be able to control the condition numbers. It's slightly more stable, the augmented Lagrangian approach, but it will also need to control the condition numbers. So if you come back to the history from the simplex method that uses exact solutions, then superlinearly convergent interior point methods, and then these methods where we don't really have much of a convergence statement, it's maybe linear convergent, and then the methods that have been proposed for the future, Frank-Wolf or conditional gradient. I think the conditioning will becoming more and more important because we're using methods that are more and more sensitive, put less and less approximation to the local model of the system. So the condition number will remain an important topic. And if I try to understand the history also, there was a dent in the development when in the early 1980s the computer switched from single precision all of a sudden to double precision, and then the interior point methods under the name SUMT that was unsuccessful all of a sudden was successful in the 90s. So a little bit of this success may be due to computer development. But here I think, especially when you come to conditional gradient methods, it's not a method of accuracy to solve the subproblems. It really is essential that we control the condition number. Otherwise, when we have a small residual, we have no information about the actual error. So this is essentially the conclusion at this point. So we need to take care of condition numbers. Thank you.
Thank you. You made it very well on time. Over at our expenses, or at my expense, because it was too big for me. So I open the floor for discussions.
So when you say that sort of this a very small number that you cannot really use, isn't that because? So why not go for high precision then?
I didn't understand.
I mean, you're complaining that you cannot solve those problems because you have a loss of precision. But if you are computing with a double floating point numbers, of course you'll hit this wall. So why don't you say that if we have to increase the precision, and then we can go a bit further.
That could be a reasonable approach. What we really have to take care of is the sparsity structure. The early methods, they were often using dense models. Now we have to use sparse models, and we cannot allow huge fill-in. And so this was also the main work of having no fill-in when we implemented the augmented Lagrangian. And when you have no fill-in, you have to use iterative methods, and they, even though theoretically they should be stopping after n steps. First of all, n is too large when you have 10 million variables. And second, it even wouldn't stop there. So it is observed that the rounding errors prevent you from reaching the full accuracy.
Point is, why just stop at double precision? Why not use quad precision? Maybe.
Yeah, but the precision, the quadruple precision, still wouldn't help with the iterative method. So the iterative method will not. I cannot afford the 10 to the 7 iterations, and even if I did, and I think quadruple precision wouldn't help either. So they break down for 100 by 100 systems. So after 100 iterations, the rounding errors explode, and after 10 million, you need precision that will kill any machine.
People tried.
I don't think they tried it. They understand this theoretically. You will not get finite convergence. And also, for the large system, the whole point is you want to be finished earlier than after 10 million iterations. So.
I don't know. Well, I mean, my experience with loss of precision is that, okay, I was approached by coding theorists who needed to solve really bad LPs, and no commercial solver was able to solve that, full stop. So, okay, I took a very slow solver that works with arbitrary precision, no problem.
Yes, and exactly. So, but I believe this slow solver probably used some exact factorization. It didn't.
It did, well, it was an LP, it did just a simplex method.
Yes, so which is an exact method. But what I'm saying is we're moving on away from the exact methods to the to iterative methods, and the iterative methods then are much more sensitive to ill conditioning. So if I use exact methods, I lose sparsity, and this is something I try to avoid here. So that was the whole point.
I think you cannot increase the precision if you want to solve large problems. You can solve small, very ill-conditioned problems.
Sorry to ask a really stupid question. This isn't my area, but these are all second-order methods, are they?
No, so if I go back to the interior point method is second-order method, and then you can argue whether the conjugate gradient is first or second order, so that's somewhere in between. It approximates a second order method, but the conditional gradient is less than first order. I mean, that is sublinear convergent.
Frank Dwarf is 0.5 basically.
Yeah, exactly. But this is actually what the development seems to go. Huge data, cheap algorithms, and this is why I was so annoyed by Nemirovsky's paper showing that that's the best you can do. So that is really not what you want to do if you develop algorithms.
Actually, I have a couple of comments because we did these things as well. So you don't use any preconditioner at all at the moment?
Right now, no.
Did you try the Morales Nossedal? So there is a BFGS preconditioner which is, as let's say, the closest thing to general preconditioner when you don't know anything about the background of the problem. And this is better than nothing.
My question was about this destroys sparsity basically.
No, BFGS, limited memory BFGS, not.
It does not.
So you just have a few non-zero vectors. And we used limited memory BFGS in some earlier version, but not as a preconditioner for the linear system. Rather, we used it directly on some smooth function, and that was not successful. But maybe if you can use it as a preconditioner for linear systems, we didn't try that one.
You construct the preconditioner by the BFGS formula from the previous iterations of the CG method, of the iterative method. does not work always. I don't claim it. It's
Okay.
a great thing, but it's better than no preconditional. I was a bit surprised by so what is your precision, the precision of the iterative method? When do you stop it? The conjugate gradient?
Termination.
The termination after 10% already. So I only wanted to have 10% in the interior point method. So the residual must be reduced to 0.1 in the norm.
Yes. And then you still need hundreds or thousands of iterations.
Yes, 40,000 iterations for this terrible problem. Sorry, for the terrible problem, it turned out that 10% accuracy was not enough. I had to go down to 0.1% accuracy. And those 0.1% accuracy, I needed those 40,000 steps.
Because we are using the augmented Lagrangian method, and also we have similar precision. And for let's say for most examples, we have less than 10 iterations per Newton system.
Yes. So this is the large number referred to the interior point approach. This is why I'm giving up on it. So for the augmented Lagrangian, this very preliminary experience was much better as well.
Yeah.
Yeah.
And just then one comment to this. So you always stress the sparsity, but in fact, I think the great thing here of iterative method is that they work for dense systems as well, because you only need this very limited precision. And even if the problem may be dense as such, so that then you just get dense matrices. But then you don't need to construct the matrix, so you don't need to store it in the memory. You don't need to compute the elements of this matrix. You just need this matrix vector multiplication. So even it works well even for dense matrices.
This is what I was saying, matrix-free and loop-free approach. So I never constructed the matrix, so I just had a theoretical matrix vector product. Yeah.
For a follow-up question, so you mentioned the tensor structure of the matrices, of the constraint matrices,
yes.
basically. And this is, and the structure is coming from the
particular application. So
application instance. It's not a systematic.
No. That was just one instance where we wanted to see using the problem structure. They actually want to have even more larger instances with 1 billion variables, and so I thought the only chance you have is you really have to sit down and do this by hand.
Okay, so there is no guideline how to proceed with the next hard instance.
No. So this is for one particular problem. Yeah.
So and if there is a different instance, then you probably have to,
change
it again by hand.
But that was one important instance for the application. So the biologists they really needed that problem.
Yeah, the structure will remain for the same for similar application problems. To be no more other remarks, questions. Then let's thank our speaker again.